Okay, so in this video, we're going to be looking at some spatial statistics. So we're going to start by loading a spatial statistics library. And again, if you've never used this before, you will need to install it first from your Tools menu. And then we're going to pull in some data from this package called Swedish Pines. And we're going to save that as X, so I don't have to keep retyping Swedish Pines all the time. And now I'm going to plot. And a lot of these base plotting functions are nice because you don't have to really know much. You just throw it in to the plot function and see what happens. And so essentially what we have here is we have a plot. We have some data points and locations in space. We could look at the data set with view, for instance, just to see what it looks like. And because it's a little bit more complex, we can't really quite peer into it very easily, but we can see a little bit of the structure. There's 71 observations, and we have values for X and Y in our format. And the plotting function is able to interpret this, even if we can't. We can sort of peek into this if we wanted and extract some of these. But for right now, this is what the graph looks like. And this is just a plot of the locations, these pairs of X's and Y's. All right, now, once we have the plot, we can also add labels. So axis 1, and we can have axis 2, and we can get a summary. So again, this will give us a little bit more of a window into what's going on here. We have a planar point pattern of 71 points. The average density is given. The coordinates are integers rounded to the nearest unit, and the window is a rectangle 0 by 96 and 0 by 100. So the area is 9,600 square units, and the unit of length is 1/10 of a meter. So again, for spatial data, you get a little bit more information. It's somewhat similar to time series data in that you get a little bit more information when you ask for a summary. So some of the metadata. Now, we plotted this as points on an XY grid, but we could also plot a density function instead to kind of smooth it out a little bit. And we're going to take a summary. So again, it's giving us some information, how big the rectangle is, again, the dimensions of each pixel, all that nice information, and then we can plot it. And we can add contours. And the add equals true is just telling it to add it on top of our previous graph and not make a completely different graph. And so again, it's by adding the contours, we have the legend here, but we also have annotations on the graph that sort of, again, highlight sort of the peaks and valleys and what those values represent relative to our legend. Now, one method of analyzing these points is to determine if the data is spatially random, if it's evenly distributed or clustered. So the analysis that we would do for this is called a quadrat analysis. So we need to create a grid in order to perform this test. So we're going to calculate our quadrat count and using x and nx equal 4 and ny equal 3. So again, this is basically taking our x's and dividing it up into 4 segments, and then taking our y's and dividing them up into 3 segments. So we have 12 total grid spaces. And again, this is just specifying essentially how many of the points are actually in each of our grid lines, in each of our categories. And then we're going to plot this. And then we're going to add our axis. And we're going to add the other axis. And then we are going to also add the grid. And it added the grid and it added the counts on top of it. Now, to conduct our test, we'll use a function called quadrat.test, and we'll conduct it on Q. The alternative hypothesis is a two-sided test, so essentially we're testing, is it random or not? And the p-value is quite high. That suggests that it is basically what you'd expect from a random distribution. It does not appear to be clustered. Now, you can actually test other versions of the quadrat test by specifying your original alternative. So you do have the default is basically would be equivalent to specifying the alternative is two-sided. That would give us exactly the same results we had before. But there are 2 other tests that we can conduct. One is if it's regular, still too high, and one if it's clustered. And again, with p-values are too high, we would fail to reject the null hypothesis in each of these cases. Now, we can look at maps and we can also do other kinds of spatial analysis on those maps. So we're going to load another package. And again, as always, if you've never used the package before, you will need to install it either by install.packages and specify the name of the package, or go to the Tools tab and install it from there. Now, when you're doing maps, you often are working with things like shape files. And this one is a package, a shape file that is included in the SF package. And so now we're going to read in that shape file. And we're going to extract two of the columns from this data. One of the variables from the year 1974 and one of the variables from 1979. VBLE2. And I believe this is a data set of sudden infant death syndrome. And so now that we have the data set up, we can now attempt to plot it. And so I'm going to pull in ggplot. And I'm also going to pull in another package. And now we're going to plot it. So ggplot. If you don't specify, then this will be assumed to be the data set. The aesthetics can be put under sub layers, not just in the top. And sometimes you have to do this even if, particularly if you're pulling from different data sets or if you want different layers to plot different things. This is just a color for the filling, and we're going to specify a theme. And so what we got is a nice map. Our variable, again, this is sudden infant deaths in 1974. We could add additional layers in order to rename the legend and add axis variables and everything like that. But this is latitude, this is longitude, this is the state of North Carolina. And you can see they had a lot in one particular county and then very little in other counties. So being able to plot maps is something that you can do in R. Now, we're also going to look at some nearest neighbor relationships. And so for that, we're going to pull in some data about Columbus, Ohio neighborhoods. This is also included in a package inside the system for one of our data packages. So we're going to load the SP data package where this data set is. And then we're also going to load one additional package. And we're going to create a map. And we're going to read in the system file about Columbus. From the package SP data. Nope, nope, not there. There. Quiet equals true. And then we can run this. Now we're going to first plot the data. this poly to NB, poly to neighborhoods, we have to specify the SPDEP because it might be masked by other packages, just to make sure that we're calling the function from the correct package. We can always specify this if we need to. And then we're going to look at the head. Again, this is just some information about how the neighborhoods are broken down. As numbers, that's not necessarily particularly helpful, but we can actually plot our map. You can see the outline of Columbus right there. And then we can plot the neighborhood data on top of it. And so the neighborhood calculations are actually calculating essentially the nearest neighbors. So which neighborhoods are closest to the other. So this is some kind of a sort of network graph that's been imposed on top of our neighborhoods within Columbus. Now we can choose the nearest neighbors by choosing one neighborhood and then color coding the surrounding ones based on their closeness. So I'm going to specify the neighborhood that I want to look at. And so I'm just going to add a note here that this is the area ID. And I can change that and replot my graph later if I want. So map and here we're going to plot it with ggplot. And you can adjust, because we're doing it manually, you can adjust these colors. manually yourself. So you could do various shades of blue, for instance, if you really wanted to. And then let's see how that runs. And so again, here's our graph of Columbus, the different neighborhoods, and then the ones that are closest to our neighborhood, 20, are shaded in dark gray or a darker gray, and then sort of medium gray for the ones that are immediately adjacent to it. And then anything that is beyond that are shaded in white. And again, you can experiment with rerunning this and changing the ID number and then seeing how all of that flows. Experiment and see what you get. Playing around with it is great to see because these neighborhoods are not, they're not displaying the numbers on them. But you can see how if you change the ID area and then you rerun this section of code, that this darker area will move as your neighborhood moves, and the amount of neighborhoods around it will also change. Now, there's a bunch of things that we can do about our neighborhoods besides just plotting them. So we could calculate, for instance, the distance from our centroid, the distance from the center. So we're going to do that calculation. And so then we're going to plot this. So we can compare the differences between the two graphs. So this one, we have connections between all of the neighborhoods. And in this one, we have only connections between those that are within a particular distance of each other. Now, there are some additional geostatistics that we can calculate, things like variograms and other things. And so let's also pull in another library. And we're going to get some data. Now, this Piranha data set is built into one of these packages. So you notice as you started typing it, it automatically comes up. And then we're going to plot it. So this is some information we have about piranhas. We have values that are plotted between roughly a little bit under 200, all the way up a little past 400. The lower values we can see are these blues, and it's shading up into the higher oranges as it goes. And we pulled out of our data set the boundaries. Again, you can expect this Piranha data set to get a little bit more information about it. And we're plotting uh, the dimensions in the northern direction this way and the eastern direction this way. So east north is X, Y. Now, what this graph is displaying is rainfall amounts. So the data set's called piranhas, but the data itself is not, in this case, is not about piranhas. Now, we can also do other kinds of specifically geostatistical graphs like a variogram. In this video, we're basically only barely scratching the surface of all the kinds of analyses that you can do on spatial data. There's so much. I mean, you could literally teach, and they do teach full semester courses for just spatial statistics and working with spatial data. So variograms are a common geostatistical plot to help understand the way that our data is behaving. As you go away in distance. Now, one last example that we're going to work on is from another data set, another data package. So we got a couple more packages to import. The SP package and the GStat package. G helps if you spell it correctly. And MapView is a popular plotting software for maps. And we're going to pull in a data set called Muse. And the grid. So here is now the nice thing about MapView is that it's fully interactive. So you can zoom in and see various things. These are zinc levels. And you can see that when they're very low, they're sort of purpley, and the places where they're very high, they're kind of yellowy, and you can see there are places in town where those levels, particularly along the water, are very high. Now the CartoDB Voyager, that's the kind of background that we're looking at. You can check the documentation for MapView to see what other kinds of backgrounds that you can use. The CRS is essentially specifying the coordinate system that is being used here. And some of these functions are just converting our data set into things that we can work with. I had a spelling error somewhere, probably. Yep, I missed my S. Here we go. And then we can also plot this in map view. So this is the gridded version of that data. Essentially, it has a dot for each city-wide grid. Now, we can also calculate the variogram on this data. Oops. And we're going to do it on the log of the zinc. And we're going to model it by essentially the constant. And so here we created the variogram. We saw one of these earlier with just the dots on it. We've added essentially a line that models the data that connects the dots for us. It doesn't really connect the dots, it models the data. And then we can also use a function to model the results, fill in the distances for us. This is essentially a type of regression on a spatial regression. And it's a kind of a Gaussian regression, basically. And so these are again, our simulations, our simulated models of those zinc levels in the city. So there's lots of things that you can do with spatial analysis. And again, I've only barely touched on some of the basics here.